Hello there. Well, this is my second video of ever how many I want to do. I am KP the Math G, and in this lesson we're going to determine continuity using limit. A couple of things that I want to address before we get into the lesson is that I misspelled approach. I'm glad that in math you don't have to worry about spelling, but you know, being 63 years old, sometimes I just misspell words. But anyway, I misspelled the word approach, and in another case, which I'm going to erase here in just a little bit, I compared on the X and Y table. I compared miles with miles. Well, really and truly, the x-axis was miles and the y-axis was also miles. And I made a statement. I didn't write this down, but I made this statement in passing. But needless to say, your x-axis needs to be more like time. So after probably 1 hour, you go up 2 yards or whatever, or 2 miles or whatever. So anyway, that's better if you do it like that. Most of the time in calculus we compare time with distance a lot of times. So anyway, just a couple of things I want to clarify, or just you know, if I make a mistake, please let me know. Sometimes I do make those mistakes, and I try to correct them on the next video. We are determining continuity using limit. I hope you can see this all right, but if I turn my light on, it will be a definite glare, so I'm trying to use my lamp over here to help me out, and I hope it does. But anyway, I have this piecewise function f, looks like a piece of a parabola and then a piece of a straight line. And so what I like to do at this time is I like to look at the definition of continuity. There are 3 things that we need to look for when we're looking for continuity. First of all, a function, say f, is continuous if f at a exists. And then b, if the limit as x approaches a from the left of f at x equals the limit as x approaches a to the right f at x. If that limit exists, then f at a, and finally third, if f at a equals the limit as x approaches a of f at x, then all 3 of these being true, then we can say that we have continuity across some interval, or however how we want to say. Sometimes we're looking at the whole thing from negative infinity to positive infinity, or we're just looking at some definite interval from, in this case, -4 to +2. When we look at this, and I had some notes on this that yes, right here. I do make notes of things that I do, so pardon me if I'm missing it. Okay. All right. So let's look at continuity. Let's take, for example, f at -3. We said last time that f at -3, this is the x value. We're looking for the y value here. The y value obviously is 0. Okay, so we'll just make a big point there. We know that this is, so f at 3 does exist. It is 0. Before we go any further, if we talk about continuity, we're saying if we can put our pencil or pen on the sheet of paper or wherever, and we draw without picking up the writing instrument, then we have continuity. And that's pretty much the idea. So here it is, we can draw this and not pick up our pencil or pen or whatever writing instrument we have. So here we go. A part, f at -3 does exist. B, let's look at the limit on the left side. The limit as x approaches -3. We did this last time from the left. We have to look at it from both sides. Remember from the left, remember we did this last time. I'm just going to put this back up again. The left of this little imaginary line here, okay, I'm just going to put that up there. There you go, right there. From the left part of this, we see then that this does approach. If we keep going this way, we run into 0. And so the only hope that we have now, the only thing we're looking for, is that if now the limit as x approaches -3 from the right, if it's 0, we have continuity. Alright, so if we go from here, we go this way, and we come down to here, then that is 0. So we know that this limit, let me write down at the bottom here, the limit, let's put it somewhere else. Sorry about that, guys, guys and girls. Where's my eraser? Would I need one? Okay. Well, okay. I forget sometimes. I knew I had it up somewhere. Okay, let's put it over here. The limit as x approaches 3. Now remember, we don't put the negative or the positive, or -3 in this case. We don't put the negative or the positive at the end because we looked at the left and the right, and then we just say, well, all of it, left and right together, is 0. So therefore this equals 0, which also equals, by the way, f at -3. So the limit equals f at -3. That's what we're looking for. I wrote it backwards, okay? And so since we have that, therefore we know then that f is continuous. We're just going to say continuous like this at x equals -3. At least we know that at -3 that f is continuous. Okay, well, we know that this whole line, this curve and this part of this line, all of this is continuous, isn't it? If we were to look at, for example, well, let's see, what else do I have in mind? If we were to also look at, let's say, -1 right here. We do have, right, same idea, right here. Alright, continuity from the left side is at 2. Continuity from the right side is, actually the limit is 2. The limit is 2. So we know then also that the limit, I'm getting disoriented with stuff. Sorry about that, guys. And I probably should have looked at the limit, the A part, the limit. No limit, I'm sorry. I'll get it right in a minute, y'all. Okay, before Christmas for sure. Okay, so f at -1 does exist. It is 2. We know that the left side is also 2 and the right side is also 2 when we talk about limit. So the limit as x approaches -1, f at x, I've already just verbally visualized that it is from the left and from the right 2. So the limit does exist. These two are the same. Therefore, we see that that f at negative 1 equals the limit. Erase this over here again. Okay. Off to a slow start today, I tell you. The limit as x approaches negative 1, f at x. So once we see those three going, then we can say these are equal. And once we can say they're equal, therefore we can say that the limit the function f is continuous at x equals negative 1. And you can even say, make a statement for negative 2. We don't know what this is. I'm saying it's a little bit below 1, but whatever it is, we see that f at negative 2 is something, and this same something is the limit from left to right is still that same something, and therefore you can tell then that the limit at negative 2, at x equals negative 2, I say the limit, we have continuity at x equals negative 2. So anywhere between negative 4 and positive 2, we have continuity here. Of course, we can't include negative 4, and we can't really include positive 2 because the graph doesn't extend beyond that. Okay. In this case, we have only a right-hand limit, and in this case, we only have a left-hand limit. So we can't really include negative 4 and 2. But needless to say, we do have continuity anywhere between negative 4 and positive 2. If you really want to get technical, we can do 1.5 or 1.25, and you can see we have that f at 1 1/3, whatever, exists. Continuity to the left and the right exists. I say limit. I'm saying continuity and limit at the same time. I should say the limit exists on both sides. Therefore, we have continuity. Okay. Alright, hopefully we have the definition in mind. I did do something on the other side. I do like my board. Excuse me. Hopefully you can see that. We're going to determine again, we're going to look at this function f. All of this is a piece, it's a piecewise function if you think about it. You have a piece here, a piece here, a piece here, a piece here, and a piece here. So it is a piecewise function. All of this is f. So what we want to do here in this particular exercise is let's determine whether the function is continuous using the limit. And of course we've already seen that if we look at negative 3, alright, so so f at negative 3 is 0. The limit as x approaches negative 3, we're just going to say from left or right for the lack of time, from this side or this side, either one, is also 0. Therefore, these two being together, we can see now that f at negative 3 is equal to the limit as x approaches negative 3, f at x. Therefore, we have continuity at the point x equals negative 3, to the left and to the right. Okay. We're going to look at negative 2 in just a moment, but I would like to look at some scenarios. Sometimes we have f at a, but we don't have a limit. And sometimes we have a limit, but we don't have F at A. And sometimes we have both, but there's no match here. So let's take a look at the scenarios that we're talking about. The next one that I have in mind is, let's see, what about F at 1? Okay, so let's see here. F at 1. What is F at 1? Somebody might say, well, it's 1 or it's -2. Remember, this has an open circle at y equals 1. And so that being true, we're looking for the solid circle. And the only one that has a solid circle is at y equals -2. So F at 1 is not 1, but it is -2. That's where the solid part is. Alright, so F at 1 does exist. It is -2, so it does exist. Okay. Now, let's look at the limit as x approaches 1 from the left. Okay. 1 from the left. And again, well, if we look at it from the left, here we go. I'm just going to kind of see if I can put together an imaginary line here. Okay. Alright, down here. Okay. From the left side of this vertical line, imaginary vertical line, this side here, we have now remember, we are talking about limit. Remember from our last lesson, even if we're talking about the limit and there is an open circle, yes, there is a limit here. It is 1. Even though this is not F at 1, the limit exists. So, okay, so the limit is from the left side, +1. Alright, let's look at the limit as x approaches 1 from the right side, though, and see if we have a match. Well, if we go down here, we're looking for that y value, and that's at right over here is -2, and I see immediately that F at 1 exists. The limits from the left side and the right side exist, but we have a problem. The limit from the left is 1, while the limit on the right, or from the right, is -2. So these two do not match. So therefore, the limit, as we see it, if these limits do not match, the limit itself does not exist. We just say D and E. Does not exist. Therefore, we do not have continuity at x equals 1. Well, it's obvious. There is a real big jump at 1. You have to jump up 1 space to get to 1. You got to jump down 2 spaces to get down to -2. You have a 3 unit gap here. There is a definite gap here. Okay, and so when you see a jump or a gap like this, there is no continuity there. Okay, right here you have it at -1. You see there's no jump, there's no gap. I can keep my pencil or pen right there and not ever have to lift it. But here I come down, I have to lift it to come over here to come down here. You see, there's a gap here, an obvious gap. Well, by the way, incidentally, there is another gap right here. Okay, so F at 3. Let's look at that. I don't mean to jump too fast at this. Oh boy. my eraser is hiding again. So, and you know, notice this time I don't have any students to hide my stuff from me. It's just me. So, okay, I got a way to erase all this. And I bet it's just right there in plain view, and somebody could probably just point it out to me. I don't see it. Oh, I bet it's on the other side of the board. You know, anyway. Let me see. I bet it is. So far I don't see it on the other side of the board either. Well, okay. Guess I'll do without it for now. Oh, there it is. I don't know. And it's not even Monday, it's Tuesday. Get that. Okay. LFAT 3. Now, it's not 1, but it is 2, isn't it? We're looking for the solid part. LFAT 3 is 2. It does exist. Part 1 is good. Part 2 is the limit. I'm just going to go ahead as x approaches 3. I'm not going to do left or right. I'll show you left or right, but what is it? Okay, so here we go. Again, right here. Okay. From the left, we see that the limit does exist. It is 1. Alright, well, we know from the left it is 1. We'll go ahead and do that. The limit as x approaches 3 from the right is, well, that's not 1, but it is, well, it looks like it's 2 or something above 2. We're going to say it is 2. It's even with 2. Alright, well, these two pose a problem, don't they? So, we say that the limit as x approaches 3, alpha at x, d n e. Wow, we don't even need to say equal. Okay, d n e does not exist. Therefore, there is, obviously LFAT 3 is not equal to the limit, since there is no limit here. Okay, and so we do not have continuity. And again, you can look right at the graph and see visually that there is an obvious 1 unit gap between the two. They're not together. I'll say, somebody may say, well, KP the math G, look at LFAT -2. And I was hoping that somebody might get to that, because that's what we have here. And I want to look at 2 more scenarios, and we'll bring our lesson to a close. Hopefully by next time I will be way more organized than this, and I thought by writing all this down that I would be, but I don't know. Okay, bear with me. There you are, eraser, right there. Now, we are looking at LFAT -2. Does it exist? Somebody may say, well, I got a hollow circle at 1. Now, remember, don't go by the hollow circle. There needs to be something solid, and there's nothing solid here. It does not exist at all. So at this point, D, N, E, okay, it does not exist. Therefore, you don't need to go any further. If LFAT A does not exist, in this case A is -2, then there's no need to look at a limit. Yes, we do have a limit. From the left side, it is 1. From the right side, it's also 1. Yes, even though we have a limit as x approaches -2, alpha at x, it is 1. We do have a limit. Don't worry about whether it has a limit or not. If alpha at -2 does not exist in the first place, then there's no need to look for a limit. And therefore there is no continuity. And somebody will say, well, it does come together, but if it comes together, it needs to be a solid, well, it needs to be solid throughout. It either needs to be a point right here. I make these points pretty big for emphasis sake. But now if you have this, now you have continuity here. Okay? Now that's good. But in our example, it was a hollow circle. And then even if we did have this existing, and if we put it somewhere else, say maybe at -3 somewhere, okay, as we pointed out before, okay, alpha at -2 does exist. It is at -3. The limit exists at 1, but here again, this does not match. Number 3 is gone. Even though number 1 is good and number 2 is good, number 3 is not, because alpha at -2 is not equal to the limit as x approaches -2 alpha at x. And yes, even though they do come, the left side and the right side limits do come together at a whole, you have to understand it's a whole. Okay? And if it's a whole, this is not existing. Oh, it's not disjointed like this or like this, but still this is not continuous. For it to be continuous, this has to be solid. Now we have continuity here. Now we do. Actually, it doesn't have to be a point. It just has to be just like that, maybe. Okay? But again, this is the key, is you have to look at all three. Okay? In this particular case, before we put the -3 down here, we did not have anything at the first. So anyway, even if you do have a limit here, and I did have a point down here somewhere, it doesn't matter. Yeah, we'll put, the point was down here somewhere like that. Well, somewhere down here. Oh, right here. But anyway, okay. Right there. It was here. Okay. Alright. Alright. That limit does not match alpha at -2. That's the point. That's the whole idea. So you can have a limit. I mean, you can have alpha at -2. You can even have a limit existing. But again, number 3, they must match. Alright, A and B must match. Okay. Alright, so what can we have? We got to have both of these together, existing, and the same number. That'll be okay. We've got continuity. We have continuity here. Look at this. At 0, we have alpha at 0 is 3. Now look at that. Alright, the limit as x approaches, what, 0? Alright, is 3. They match. So then, alpha at 0 equals the limit as x approaches 0. Alpha at x. So we have continuity. Therefore, we have continuity at x equals 0. We're good here. And we're good here. We have continuity here. But we don't have continuity as far as being at an integer. We have continuity between -3 and -4. We have continuity between -3 and -2, and so on. but we just don't have continuity everywhere on F. F is not continuous everywhere. Okay? So we are looking at continuity at a particular point. And sometimes when we look at calculus, we look at little pieces of puzzle. And then we put it all together. Now, if it says, is F continuous everywhere? The answer is no. It's not everywhere. Yes, it is at some places. When we look at the integers here, 0, at 2, and in between, of course. But if we're just looking at integers only, we have continuity there. Okay. So keep that in mind when we're talking about continuity. Okay. Excuse me for losing my eraser, and I tried to be organized with this and everything. I hope you found the lesson still to be profitable. I enjoy lessons like this, but then from this point on, we're going to, instead of looking at the graph part of it, we're going to look at the algebraic part of it, and that will be on the next lesson. This is the second of the first two lessons that deal with limit, so the next one will be determining limit algebraically if the limit exists. Okay, so thank you for your time. I appreciate you very much, and I hope you keep tuning in to my videos. Thank you.